Hello, I'm Jonathan Friend. I'm a mission concepts engineer from Surrey Satellite Technology, and I'm here today to talk to you about the use of the Lunar Communications Pathfinder services for CubeSat missions. Okay, so this is a partnership that we've been working on for a while. So it's Surrey Satellite Technology and Goonhilly Earth Station, in partnership with the European Space Agency, proposed a set of commercial lunar mission support services with the aim of developing vital infrastructure for underpinning lunar exploration. So each different party in this partnership brings something different to the table. So with European Space Agency, they're providing expertise and understanding all the different processes service. Goonhilly are bringing the ground segment, so with their site in Cornwall, we're going to be using one of their very large hosting dishes, and they're also going to be developing an operating centre and using services down there as well. And Surrey Satellite Technology will be providing the space segment and integrating so the first phase of the partnership we're working on at the moment is really mainly focusing on the ground segment. So Goonhilly are in the process of receiving funding from the local UK government, industry and private investment with the aim of upgrading the largest antenna to be able to be compatible with S and X band near and deep space communications. So this will be actually providing cross support to the ESA S-Track network as well, so essentially extending that network. And in this phase as well, SSTL are maturing the design of the space segment and looking at various different studies for implementing payload accommodations and supporting certain types of lunar missions. So phase 2, the Lunar Services Pathfinder. So this will be the first actual mission to the moon, and we'll be working on a ride and phone home integrated service package with pricing on a per kilo basis. So this is an all-inclusive package which will include integration of payloads into the Pathfinder spacecraft. So these can be CubeSats, solid nanosats, even basic payloads which would remain on the Pathfinder spacecraft. So they would be integrated in a facility in Guildford, and then we would launch the spacecraft and deliver these payloads to lunar orbit. And there would be some level of cooperation between the potential customers and us in terms of actually working out which orbits we can deliver these payloads into within reason. So there's a certain allocation of propellant budget to actually enable us to access several different orbits for different customers. And the communications relay services, which will be working on store and forward architecture, so primarily based around the UHF proximity 1 protocol, and possibly if there's interest, we'll look into implementing an S-band version of proximity 1 as well. And then we'd be aiming to demonstrate some initial navigation services on this first mission, and those concepts are still being worked through. Also, there would be an application programming interface providing a transparent interface to the customers. So really, CubeSat operator will only use a piece of an internet connection to be able to actually operate a mission around the moon. Yeah, so the core of the comm service is the proximity one UHF service, which has various benefits. This service has been implemented around Mars for the last 15 years. So both ESA and NASA satellites have been providing comm support with proximity one to various NASA and rovers and landers. So it provides dynamically adjustable data rate from 1 kilobit per second up to 2048 kilobits per second. So this really covers the full range of basic telemetry all the way up to potentially streaming video, and can be dynamically adjusted during the course of the week. And the main benefit of UHF is the fact that the free space path loss is significantly lower than the next allowable applications in excellent so this means that missions can be undertaken with omnidirectional antennas, which provides a certain level of operational flexibility. So the proximity one service provide autonomous multi-user communications, and will be shared out by providing certain time allocations, which will be cycled through in a certain cycle period to make sure everyone has a fair amount of time. And in implementing this autonomous communication, we will aim to maximize the data throughput for each customer by trying to select when they get their allocations to when they have the best time. Okay, so to model the likely scenario and get an idea of the representative communications traffic, put a scenario together mainly based around assets with quite low performance communication systems. Systems that are quite common in CubeSats and other resource limited spacecraft. And then have a look at distributing these assets around different orbits. So reflection of a couple of assets in highly elliptical lunar orbit, some in a lower elliptical lunar orbit, low lunar orbit, and then 2 landers as well. So the proximity one, as I said, it provides a great deal of flexibility, particularly because of the use of UHF and the use of the braided altogether. The Pathfinder spacecraft doesn't need to know where any of the users are to be able to actually provide communication support to them. So in the simulation, we're assuming that all of the assets don't alter their attitude at all to be able to communicate, and the Pathfinder spacecraft is essentially negative pointing, and the beam is sufficiently wide for that to happen with the users. So to commence a link, the Pathfinder spacecraft will hail the individual users by a specific spacecraft ID, and it will cycle through these and select the spacecraft which has the best route at the time, and then will provide comm service to that until the link session ends. And this could be for a number of reasons. It could be the end of the time allocated to the spacecraft, or it could be that the spacecraft is communicating with an elect to end communications link, so they have no more data to send across, or if the Pathfinder goes out to the other spacecraft, so if it's crossed behind the main, can obviously no longer maintain command. And so this graph here shows the throughput over the course of several days from the list of users that we showed in the previous slide, and rates here that can be achieved by these CubeSats up to 256 kilobits per second. So, as I said previously, the comm systems we assumed on the assets were really quite low performance. And the services shared out by chunks of time. So the actual achievable data rates are really dependent on the actual comm systems on board the individual spacecraft. More capable comm systems would be able to provide users with much higher data rates for the same amount of allocation. So for instance here, the same length over the same time period for the same user has been modelled twice. Once with a linearly polarised web antenna, which is quite common for CubeSats operating LEO, and one with a circularly polarised propagation, which provides less losses over the link. And this shows that, despite the peak rate not actually improving, the mean data throughput is actually a lot higher because more of the time in each of those link sections is actually at a higher rate. So this is quite a basic example of how the rates can be improved, but adding slightly more directional antennas, getting some amount of steering of those antennas, or increasing the transmit power would also serve to significantly increase the data rate. So one of the key benefits of having a communications relay auditor is the fact that we can extend the coverage of communications over a system relying on direct-to-earth communications. So, for instance, in this example, we have in this graph plotted the links back to Earth, and then the links from an asset in the lunar orbit to the relay spacecraft. This is showing in a couple of instances here where a link has continued, where the link would have dropped out on a direct-to-Earth link. So this is when the spacecraft has actually been passed behind the link, and this link has been able to continue because there has been a relay network. So another real benefit of the system in terms of operational flexibility is the store and forward architecture. So this really provides kind of operational flexibility, risk reduction, and a higher throughput than bent pipe type systems. So where bent pipe systems rely on there being simultaneous access between the asset, the relay orbiter, and the ground, the store and forward type approach can really keep working all the time to keep the data coming from assets, and then can also conduct the mission with less ground support if it needs to. So commands can be sent to the ground station, wait there until the next access with the Pathfinder, then upload to the Pathfinder, and then they'll sit there in the storage until the next access to a particular asset where those commands are headed. Similarly, the data coming from the asset could be stored on the Pathfinder until the next ground access. So in the current architecture for the Pathfinder mission, it's assuming a single ground station. So this can be up to 16 hours between ground station accesses, then probably 8 hours of continuous support. So in this architecture, really quite a lot of the data is being gathered when there is no ground station in view. So this rocket shows the amount of data being transferred in red where there is a ground access, and in blue where we're between ground accesses. So a key benefit in terms of risk reduction with this approach is that if you're relying on a vent pipe system and between accesses your spacecraft has failed, there's more likelihood, no way of knowing how that's failed, and it would likely be loss of motion. Whereas with this system, you are still getting a steady trickle of data through between accesses, so you would have a record for the telemetry which has come from the spacecraft over that time. So potentially, by accessing that data that's been sent to the relay orbiter, you could go through and work out what the likely causes of failure are and potentially rectify the problem. Also, the requesting data from a spacecraft, where the bottleneck is the link between the Pathfinder and the user asset, will mean that if you're trying to request lots of data when there is a link all the way through the system, you're going to be doing it at a very low rate. Whereas this way around, as soon as the ground station accesses the Pathfinder, all of the data that has been collected over the last 16 hours from the asset could be with the users in a matter of minutes. So all of that data would be there ready for them to run through and plan out the next set of operations for that So also, in many types of missions, there'll be a phase where you really need to guarantee that you've got a lot of communication support. So particularly if there are critical maneuvers to perform or a series of really key scientific experiments that need to be done with a lot of supervision or a much higher amount of access to the spacecraft. These phases can be built in by basically increasing the amount of overall time allocated to a certain asset. So here, by changing the priority level to the same asset, you can see sort of around about a fourfold increase in the amount of data throughput and significantly increased constant duration. So this sort of approach could be done for a short period of time where there are these critical maneuvers or science experiments, and then afterwards they would go to a lower level of support for such time as the rest of the users using the system have been compensated for the time they've lost out during this phase. So the idea is that we will be using these systems we're developing called Pathfinder to then, in phase 3 of the program, gradually start building up a constellation around the moon to make sure that we have these services available for more of the lunar surface, and we'll be able to provide support for more assets at longer durations and higher data rates, and gradually fold in new advancements in the technology and look at new architectures, possibly involving the ranging points and higher throughput technology. And yeah, that's the point. Do you have any questions?
Any questions?
You mentioned risk reduction, and certainly if you have a constellation of them out there, then that's a great way to do that. But initially, how would you convince your customers that you're not putting all your eggs in one basket? Would you plan to make selective redundancy or full redundancy on the Pathfinder in order to mitigate those risks?
So the Pathfinder would be fully redundant to start with anyway. I think that's classically how we design our spacecraft. and there's nothing stopping customers from having both the direct to Earth and a relay communication system. In fact, that could be good in lots of ways, but like with a lot of the rovers on Mars, they'll have an X-band direct to Earth communication system and the UHF proximity one. And they found that actually most of their data is actually done through the proximity service because of the simplicity in using the service, and actually high data rates and things like that. Because you're effectively aggregating the data and then communicating with the single hub spacecraft, which is taking the data from the lander or rover and itself. So it's in terms of ground signal support, you get kind of more data through by using the dedicated comms asset.
So is there any plan to you think about applying this concept to Mars to support multiple CubeSats over there?
Yeah, eventually it is on our roadmap to gradually expand the service and apply what we've been doing to the moon to Mars as well. But I think in the near future, the moon is going to be the more likely destination for more customers, because it's mainly because of its proximity. You can get launch opportunities every month potentially, whereas you've really got that one slot every 2 years with Mars. So we really see the moon as kind of that area for kind of rapid access and testing out technologies, and also if you look at the economics of the situation, it's not hugely clear how money will be made from Mars yet. It would be a great humanitarian effort to get there and establish bases and things, but really, in terms of economics, there are much clearer ways in which we can start developing infrastructure in the moon and start making money from extracting resources and then actually servicing the terrestrial market with the ability to extract the money. Yeah, essentially yes, we would be looking at, but it's certainly in the longer term.
I may have missed it, but you must be making some assumption about the time between contacts between the Pathfinder and the assets, minimum time, and how long a likely gap there would be between, being in range and not on the opposite side of the moon from each other. And I'm concerned about how that might affect, particularly on the uplink side, because if it's undetermined and you need to get a sequence up, you just have to allow, is it a day or what?
Oh no, so we, it's basically run autonomously with this algorithm that kind of goes through the different spacecraft and work out when you've got good links. But the cycle, like I talked about briefly, I didn't go into much detail on, but effectively we keep the cycle reasonably short, so you're guaranteed accesses, numerous accesses within that cycle, and that cycle may be 8 hours or something like that. So
doesn't that depend on the orbits of the assets though?
It does, but basically what we do is we poll all the assets that we know we're servicing, and when if they don't respond, we just move on to the next one. So you basically, it also helps by providing most of your actual time allocation during times when your link budget is more favorable. So your accesses are going to be happening when you have a shorter distance or things like that. So yeah, you're getting accesses, several accesses within each cycle, and the cycles are short enough that you will be getting frequent enough access. And then it's just done on best availability. That way it means that it's a lot simpler operationally as well. That with the store and forward approach means that you can just upload a load of your commands and wait for everything to go through and then get all your data back.
Thank you. Thank you for your interesting presentation. I completed the question. Please you could return to slide number 5. You did that you share the access to the slide autonomously. Okay. How you could reach this autonomous multi-user communication?
Sorry, is the question, how do we achieve the autonomous communication?
Between users.
Yeah, okay. So each individual user will have its own unique spacecraft ID, and the link is always initiated from the Pathfinder spacecraft. So what we will do is effectively, when it's time to access a new user, so if at the end of a time allocation, the link is dropped out from the previous user, we'll then poll all of the users that we have in our list and select users which have the strongest signal. And then once they've had that time allocation, then we'll poll the rest of the users. And basically, it's an algorithm that basically works through all of the users that we have and tries to match the times when we communicate to the times when they have the strongest signal.
We must have this synchronization between users, the cycle, the time allocation.
Sorry?
Synchronization, each user get allocation time.
So it will be managed autonomously on board the spacecraft. So we'll upload kind of what the time allocations are supposed to be for each spacecraft, and then the payload of the Pathfinder will then cycle through all the assets and give them the appropriate time allocations.
And there is no time constant. The range is too high.
I think maybe if we continue this discussion offline and break that.
Oh yeah.
Thank you very much.
I think there's one last question up there.
Right, so in your consortium, there's ESA, who's providing some ground operations with Goonhilly, which is an antenna, and then there is Surrey, which is flight segment. What about the launch segment? How do you get there?
So we've been, as a company, commercially procuring launches for the last 30 years or so. So that's something that we do quite often. In fact, in the past, we've even provided launch acquisition as a service to certain customers who have their own spacecraft. So,
Yeah, this is beyond doubt. We all know this is a record, but is SSTL paying for launch?
yeah, so the whole point of the thing is that it's all being approached commercially, so we will be paying for the launch and paying for the operations and yeah, we'll be doing commercially.
Okay, thank you. Well, in that case, let's thank our speaker.